Hi friends, in this video I am going to explain you the evaluation of in-plane and flexural constants of a laminate using ANSYS Workbench. The laminate stiffness can be defined by using the laminate engineering constants. So the in-plane engineering constants of a laminate is nothing but the effective in-plane longitudinal modulus, effective in-plane transverse modulus, effective in-plane shear modulus, effective in-plane Poisson's ratio. And the next one is flexural engineering constant of a laminate. Effective flexural longitudinal and transverse modulus, flexural shear modulus, and flexural Poisson's ratio. So in composite, we can write the resulting force and moment in matrix form by using ABD matrices. Okay, so here this is a given equation in matrix form. So N and M, here the strain and curvatures. Okay, so N is resulting force and M is the resulting moment. So this is a combined ABD matrix. So by using this equation, we are going to find out the in-plane constant and the flexural constant of the laminate. Okay, so we can write the relationship in short notation. So this is a short notation of the previous equation. Okay, so the extensional stiffness matrix relates the resultant in-plane force to the in-plane strain. The bending stiffness matrix relates the resultant bending moments to the plate curvatures. And next, the coupling stiffness matrix couples the force and moment terms to the midplane strain and midplane curvatures. Okay, so by using that relationship, here we can write the equations for the effective in-plane longitudinal modulus. The next one is to find out the effective in-plane transverse modulus, we can use this equation. Then to find out the effective in-plane shear modulus, we can use this equation. The right side, you can able to see the effective flexural modulus formula and effective flexural transverse modulus and effective flexural shear modulus formulas you can able to see. So in both the sides, you can able to see the A star and D star. The A star and D star matrices are called the extensional compliance matrix and bending compliance matrix. Okay, so here the A11 star, A22 star, A66 star are nothing but the components of the extensional compliance matrix, whereas the D11 star, D22 star and D66 star is nothing but bending compliance matrix. Okay, component of bending compliance matrix, which is nothing but the total thickness of the laminate. Okay, so in this video I am going to consider one example problem. So I am going to use the same material property which is used in the previous video. So nothing but graphite epoxy. So this is the material property of the graphite epoxy lamina. Okay, so here we are going to consider one laminate which is having 0 degree, 90 degree and another 0 degree. So we can call it as a 3-ply symmetric laminate. We open the ACP. The first one we supposed to define the material property for our composite laminate. So go to engineering data source. So I have already defined the material property for my laminate. So assign the material. Here the structural steel is not required, so disable it. Close the engineering data. Next I am going to create one geometry to find the in-plane and the flexural stiffness. So I am going to use new design modeler geometry. So select XY plane, then select normal to view. So I am going to create one rectangular geometry by using sketching. Go to sketching, then select a rectangle, Then I am going to draw one rectangular geometry here. Okay, next I am going to define the dimension for my rectangular geometry. I am going to define the length and width of the geometry. So length I am going to consider as 0.1 meter. Width I am going to consider 0.02 meter. Okay, by using this rectangular geometry, so I am going to create one surface body. So for that, go to concept, select surface from sketches. Okay, then select the figure and apply. Then I am going to select the add frozen. Then we need to define the thickness of the surface body. So it is 5 mm, so therefore 0.005 meter. Okay, then press generate. So you can able to see one surface body which is created from the sketch. Then go to model. So basically the model can be used to convert the CAD model into FEA model. So select edit. Okay, if you look at the under geometry there is one question mark. It means we need to assign the material for our geometry. So therefore select the surface body. So the bottom, so you can able to see yellow color. It means we need to assign the material. Okay, now we can able to see question mark is disappear. Okay, next I'm going to do the mesh. So for that I'm going to use the default mesh size. Right click and generate mesh. Okay, so this is our FEA model of the geometry. Okay, next we need to update it. Right click on the model, then select the update. Okay, so next we need to move on to the setup. Right click on setup, edit. Okay, here you can able to see your geometry. So this is our geometry. If you want to see the mesh, you can select the mesh there, then press update. Okay, so now you can able to see your model as in blue color. Okay, go to material data. So we need to define the material and thickness for our lamina using the fabrics. So right click on the fabric and create fabric. Okay, so here you can able to see, you can select the material. And the next you can define the thickness of our lamina 0.005. Then press apply. Give OK. Next, our ultimate aim, we need to we are going to find out the in plane and flexural stiffness. So for that we are going to create the stack up. So we need to select the stack ups. We need to define the stack ups. So right click, create stack up. So under fabric we are going to define each lamina. So let us consider this is the lamina 1, the lamina 2, and lamina 3. Lamina 1 is 0 degree, lamina 2 is 90 degree, and lamina 3 is 0 degree. Base of symmetry, laminate. So go to analysis. Okay, go to CLT analysis. So select the laminate stiffness and compliance matrix. So just press apply. You can able to see the ABD matrix which we already discussed in the previous video. So this 3 by 3, this 3 by 3 defines A matrix. So this 3 cross 3 matrix define the B matrix, and this 3 by 3 matrix defines the B matrix. So here this 3 by 3 matrix defines the D matrix. Okay, so this is called the stiffness matrix. So below to the stiffness matrix, you can able to see the compliance matrix. Compliance matrix. So nothing but inverse of A matrix, B matrix, and B inverse transpose matrix and D inverse matrix. So this is the compliance matrix. Okay. So next we need to get the engineering constants. So go to CLT. Okay. Select laminate engineering constants. Okay. Just press apply. You can get all the details of the in-plane and flexural constants of a laminate, which we have defined. So this is nothing but, see, if you look at that, so laminate stiffness E1, so means nothing but EX. Next laminate stiffness E2, EY. This is nothing but EY. Okay. Next you can able to see laminate shear stiffness. Okay. So this is the shear stiffness. Okay. So next this is the flexural laminate stiffness. Okay. So this is the value. Next one, flexural laminate stiffness. The last one is flexural laminate shear stiffness. Okay, these are the engineering constants of our defined laminate. So here by using the analytical equations, we can find A matrix, D matrix. Since here the laminate is symmetric laminate, so we supposed to keep it in our mind. The B matrix should be 0. For symmetric laminate, the B matrix should be 0. On the right side, we can call it as the extensional compliance matrix, that is nothing but A star, and bending compliance matrix, nothing but D star. So these are the obtained in-plane engineering constant and flexural engineering constants using equations. So here the Ex, Ey, Gxy is nothing but in-plane engineering constant value, and Efx, Efy, Gfxy is nothing but the flexural engineering constants, which is obtained from the analytical equations. Okay, so this is the results obtained by using ANSYS workbench. So the top one is stiffness matrix and bottom one is the compliance matrix. Okay, so the blue color indicates the A matrix, the red color indicates the B matrix, green color indicates the D matrix. Okay, same like that in the compliance matrix, the blue color indicates the A inverse matrix, and red color B inverse matrix and B inverse transpose matrix, and the green color shows the D inverse matrix. So these are the results obtained from the ANSYS workbench. Okay, so in this slide, I want to show you the comparison between the ANSYS workbench and analytical formula. The left side ANSYS workbench results, right side analytical results. If we can compare the results. The inverse matrix which is obtained from ANSYS workbench. The right side compliance matrix. Okay, so if you look at there, all the values are closer to each other. Okay, the bottom you can able to see the engineering constants value which is obtained from ANSYS workbench. The right side engineering constants obtained from analytical formula. Okay, the red color shows the flexural constant, whereas the blue color shows the in-plane constants. Okay, so why this way we can compare the analytical and the ANSYS workbench results. In next this is very important. Okay, for unsymmetrical laminates, the stress strain relationship in the given equation are not uncoupled between force and moments. Okay, so therefore what will happen? The effective in-plane stiffness constant and flexural constants are not meaningful for these cases. Okay, so we have to remember this thing. So it means we cannot able to use whichever the equations we follow to find out the in-plane and flexural constants. not applicable for the unsymmetrical laminates. We have to keep it in our mind. Okay, so this is the reference book I follow. Thank you for watching this video. Thank you, friends.